In this video, we're going to look at solving trig equations by squaring both sides. So when you square both sides of an equation as a step in solving the equation, you may introduce solutions that don't solve the original equation and therefore must be excluded from the solution set. These extra solutions are known as extraneous solutions. For example, if we start with a very simple x equals 2, for which the only solution is 2, if you square both sides, you get x squared equals 4, which has two solutions, 2 and negative 2. So we would say in this case that negative 2 is an extraneous solution. So I'm going to slide this up and let's see how this is going to work in the context of some of these trig equations. So we're going to solve over the domain 0 to 2 pi. You see in this trig equation, cosine x plus 1 equals sine x, that we have two different trig functions. So this one is a little bit more challenging. In fact, probably the most challenging kind of problem we'll see. We can't trade in one for another, and we can't really isolate one and be able to meaningfully tell what the solution set is. So since we do know our favorite trig identity, sine squared plus cosine squared equals 1. These involve squares, so that's why we are going to, let me change colors here so we can still see the original. So we're going to square both sides of the equal sign here. Now be careful, on the left side that is not just cosine squared x plus 1. This is our a plus b squared, which is going to be the first one squared twice the product plus the second one squared. So that's going to be cosine squared x plus twice the product is 2 cosine of x plus the second one squared is 1. And on the right side, we'll just get sine squared of x. So from here, we can see that we still have two different trig functions, and we would like to get this to be just one trig function. So on the right side, if we replace this sine squared by 1 minus cosine squared, remember that comes from our favorite trig identity. If we subtract the cosine squared to the other side, sine squared is equal to 1 minus cosine squared. Then we have finally gotten to a place where our equation has only one trig function. So now we can proceed. I'm going to add the cosine squared to the left side, making 2 cosine squared x. We still have that 2 cosine x. We subtract the 1's and they'll drop out, and that gets us to 0. We can now factor out the greatest common factor of 2 cosine x, which will leave behind a cosine x plus 1. So from there we get either the 2 cosine of x is 0 or the cosine of x plus 1 is equal to 0. Dividing the first one by 2, we get cosine x equals 0, and so x can be pi over 2 or 3 pi over 2. Both of those will make cosine equal to 0. From the second equation, we get cosine x equals negative 1, and between 0 and 2 pi, the only place where cosine is going to be negative 1 is going to be at pi. Now, before we pat ourselves on the back and go on, we need to view these solutions with suspicion. Because we squared both sides as an operation, these one or more of these may be extraneous solutions, and the only way we can tell is by going back to the original, which remember is in the green, and plugging them in and seeing if it makes that a true statement. So we will test first pi over 2. That would make cosine pi over 2 plus 1 equal to the sine of pi over 2. I'm going to write a little question mark because that's what we're trying to tell. Now cosine of pi over 2 is 0, so the left side becomes 1. Sine of pi over 2 is 1, and that is a true statement, so pi over 2 is going to be a valid solution. So we have to also check 3 pi over 2. So that gets us to cosine 3 pi over 2 plus 1. We're asking the question, is that equal to the sine of 3 pi over 2? But here we'll see cosine of 3 pi over 2 is 0, making the left side 1, but the sine of 3 pi over 2 is a negative 1. That's not true, so that means that 3 pi over 2 is extraneous. It has to be rejected. And then we still have to check pi, and if we plug that in, we're going to get cosine of pi plus 1 equals, maybe, sine of pi. And the cosine of pi is negative 1, and the sine of pi is 0, and that one does check out. So our final solution set is going to be, we have pi over 2 was valid, and so was pi. And we rejected the 3 pi over 2 as extraneous. Okay, let's look at this next one. Now, this is, there's a couple ways you can do this. You can square both sides right off the bat, and that is perfectly legitimate. And you'll just have to use our identity with the trig functions that uses cosecants and cotangents. So we would have to take that sine squared x plus cosine squared x equal to 1 and divide through by sine squared to create 1 plus cotangent squared x equals cosecant squared x. Or alternatively, and I don't know, this might be easier, we could rewrite this in terms of sines and cosines, and then use this strategy of multiplying through to clear denominators. So if we multiply through by a sine x, we can cancel those denominators. So the first one would become just 1 on the left side. The sine x times 1 will be just a sine x, and the sine x times a negative cosine over sine is going to become a negative cosine. So now we can square both sides. We have the same issues we did before, where we have two trig functions and neither one of them is squared. So in order to be able to do anything meaningful, we have to square both sides. I would personally add the cosine x to the other side first. Otherwise, you're going to create a sine cosine term, which we can deal with, but it might be easier to just square them when they're on separate sides. So that is now going to give us on the left side the first one squared twice the product plus the second one squared, and there's our sine squared. As we did in the earlier problem, we're going to replace again. These start to look a lot the same, many of them. We'll replace the sine squared by 1 minus cosine squared. Again, we're going to get 2 cosine squared x plus 2 cosine x. The ones will subtract off. We will factor out the greatest common factor. And again, we're looking at 2 cosine x is 0, or cosine x plus 1 is 0, making cosine x equal to 0, or cosine x equal to negative 1. And for cosine x equal to 0, our choices are pi over 2 and 3 pi over 2. And to make cosine negative 1, we're back to pi. So let's try plugging those now in. And to plug them into our original, we're really going to look at our version of that has the sines and cosines. So for pi over 2, if we plug in the pi over 2, we're going to get 1 over the sine of pi over 2. Is that equal to, perhaps, 1 minus cosine of pi over 2 over the sine of pi over 2. Sine of pi over 2 is 1, so 1 over 1 is 1. And the cosine of pi over 2 is 0, and 0 over 1 is 0, and so that does check out. So I'm going to come up here and say pi over 2 is going to make it into our final solution set. Now if we check out the 3 pi, I don't have much room. I'm going to go sideways here. I can create some space this way. So let's look at 3 pi over 2. So we're going to have 1 over sine of 3 pi over 2 maybe is equal to 1 minus cosine 3 pi over 2 over sine 3 pi over 2. So sine of 3 pi over 2 is negative 1. We have 1 minus cosine 3 pi over 2 is 0, and that's not going to work, and so that makes 3 pi over 2, again, extraneous. And if we check out pi, we're going to get 1 over the sine of pi. Is that equal to 1 minus cosine pi over the sine of pi? But we have problems here because the sine of pi is 0, and that's not defined. And so that means that cannot be a solution. So it too is extraneous. And in this case, we have only one good solution, and that's going to be our pi over 2. So it is the only solution. And it could be that none of them work and we get the empty set. Okay, let's try another one. Here in yellow, we have sine x equals cosine x. So we can square both sides. That's going to give us just sine squared x there and cosine squared x there. So we can trade one in for the other. I'll just keep the sine and trade the cosine squared in for 1 minus sine squared. If I add the sine squared x to the other side, that's going to give us 2 sine squared x equals 1. We can divide through by 2. We can square root both sides, and we want all possible solutions. So remember, the square root of a fraction is the square root of numerator over square root of denominator. That's going to be 1 over square root of 2. And if we rationalize that, that's going to be square root of 2 over 2. So the values of x that will make sine x equal to either a positive square root of 2 over 2 or a negative is going to be all the angles whose reference angle is pi over 4. So pi over 4 in quadrant 1, and 3 pi over 4 in quadrant 2, 5 pi over 4 in quadrant 3, and 7 pi over 4 in quadrant 4. But we got to check to see if these are really valid. So when we check pi over 4 in the original, is the sine of pi over 4 equal to the cosine of pi over 4? Question mark. Yes, because they're both a positive square root of 2 over 2. So our solution set is going to include a pi over 4. If we try 3 pi over 4, now we're going to have a problem because the sine of 3 pi over 4 in quadrant 2 is a positive square root of 2 over 2, but the cosine in quadrant 2 is negative, so that makes that extraneous. And if we try 5 pi over 4, then you may see where we're going with this. Sine of 5 pi over 4, is that the same as cosine of 5 pi over 4? Well, they're both a negative square root of 2 over 2 in quadrant 3, and so in this case they are good, and so they are in agreement. So 5 pi over 4 also makes it into our solution set, and 7 pi over 4, we're going to have a problem once again, because this time in quadrant 4, the sine is going to be a negative, and the cosine is going to be a positive, and that's going to make that be extraneous. So our final solution set includes just pi over 4 and 5 pi over 4. All right. Let's come back to do some factoring. So here we are solving again from 0 to 2 pi. Now here we have two different trig functions, but unlike the problem we just did, one of them is already squared. That means it's easy for us to trade in that cosine squared for something involving sines, namely 1 minus sine squared. And the rest of it is just going to hang in there, and we're going to try to factor this. So I like to make the square positive, so I'm going to add the sine squared to the right side, keeping the 2 sine x, and the 1 plus 2 subtracted over, when I move it to the other side, I think that's going to be a minus 2 sine x. And then the 1 plus 2 is 3, subtracted to the other side is going to be a minus 3. So we can do our box and diamond. Remember, we want to multiply to be 3x squared, and we want to add to be a negative 2x. So that is going to be a negative 3x and a positive x. we do our box, and we put the x squared in one corner, the negative 3 in the other, and negative 3x in one side and the positive x on the other. We'll get x here. That's going to need to be an x up there. That'll make this be a negative 3. That'll make this be a positive 1. And they agree in the right corner. So our factorization is going to be x plus 1 and x minus 3. So that's going to make x be, or sine x, sorry. Let me come back and go back to our signs. So that's the sine of x, what did I say, plus 1, and the sine of x minus 3. Now we're going to set these each equal to 0. So sine x minus 3 is 0, sine x plus 1 equals 0. So when you get sine x equal to 3, that's a bit of a head scratcher. But if you remember, the biggest sine can ever be is 1. There's no value of x that's going to make sine equal to 3, and so that contributes nothing. On the other hand, the only thing that makes sine x negative 1 in between 0 and 2 pi is going to be 3 pi over 2. Now we better check and see if this really does work. So back in the original, so I'm coming back here, the cosine of 3 pi over 2 squared plus 2 times the sine of 3 pi over 2 plus 2, is that equal to 0? Well, the cosine of 3 pi over 2 is 0, so that's going to be 0 squared, plus the sine of 3 pi over 2 is negative 1, so that's going to be 2 times negative 1 plus 2 is 0. I think we can convince ourselves that that works. So we do actually get one solution, 3 pi over 2, for that equation. Okay, let's do the next one. So again, we're going to trade the sine squared in for 1 minus cosine squared x, and we still have that 3 cosine x. Distributing will make that 2 minus 2 cosine squared x plus 3 cosine x is 0. I'm going to stick with my strategy of making the squared term positive. That means that the cosine will become negative, as will the 2. We can do our box and diamond, and so that's going to be a negative 4x squared and a negative 3x. So I think we're going to get a negative 4x and an x. So that's going to give us our, what did I say, 2x squared, I guess is what we had. 2x squared, a negative 2. We got a negative 4x and a positive 1x. So we're going to have a 2x and an x. Is that right? I'm going to do that the other way. Let's call this the x and this the 2x. That would make this the 1 and this the negative 2, and that's going to work for us. So that's going to become, what do we got, cosine x's, I guess. So let's call that cosine x minus 2 times cosine x plus 1 is 0. We've seen this now before, that we're going to get on that first one, cosine x is equal, cosine of x is equal to 2, but the biggest cosine can ever be is 1, so that's not going to give us any solutions. Cosine x is negative 1 when x is pi. We'll check it back in the original. So in that original, 2 sine of pi squared plus 3 cosine of pi, is that equal to 0? Sine pi is 0, and cosine pi is negative 1, and I don't think that's going to be 0. So that means our only possible solution we just rejected. That means in this case there is no solution. Interesting. All right, got another one for us here. Again, we're going to trade the cosine squared in for 1 minus sine squared x. Everything else is going to stay the same. It's going to be 4 minus 4 sine squared x minus 4 sine x is 5. I'm going to move everything to the right side, so that'll be a 4 sine squared x. That'll be a plus 4 sine x. Subtracting the 4 from the 5 will make that 1. We can do our box and diamond again. So we've got 4x squared and 1. So I think that's going to be a 2x and a 2x. So for us, that means 2 sine x. Oops. I guess I should go all the way. I'm kind of jumping the gun here a little bit, but I have an idea where this is going. So we're going to go 2x and 2x. That's going to be 1 and 1. So that's going to be 2 sine x plus 1 times another 2 sine x plus 1 equals 0. The only solutions, if there are any, will come from 2 sine x plus 1 equals 0, which means sine x hopefully is going to be negative a half. The angles that make sine x negative a half, in quadrant 1, the reference angle is going to be pi over 6, and sine is negative in quadrants 3 and 4. So that's going to give us 7 pi over 6 and 11 pi over 6. We have to check those. So if we try 7 pi over 6, that would lead to 4 times the cosine of 7 pi over 6 squared minus 4 times the sine of 7 pi over 6. Could that possibly be equal to 5? So we have 4 times cosine of 7 pi over 6. Let's see, cosine of the reference angle pi over 6 is square root of 3 over 2. And in quadrant 3, that's a negative, but we're going to square it. So that's going to be 4 times a positive 3/4, which will be 3. And we've got minus 4 times the sine of 7 pi over, that's supposed to be 7 pi over 6. So that's going to be, the reference angle again is pi over 6. Sine is a half, and quadrant 3 is a negative. So that's going to be a negative 1/2. And that's going to get us to a positive 2. And how about that? It works. So one solution is going to be our 7 pi over 6. I wonder what the chances are for 11 pi over 6. So we're going to go with 4 cosine of 11 pi over 6 squared minus 4 sine of 11 pi over 6. Is that possibly equal to 5? So again, 11 pi over 6 has a reference angle of pi over 6. That's going to get us a square root of 3 over 2. Squared is going to be 3/4. So that's going to be 4 times 3/4, which is going to be 3. And then we're again going to get a minus 4 times, and in quadrant 4, that's going to be also a negative 1/2, which is going to be a positive 2. And that is, in fact, equal to 5. They both somehow made it. And so that is our solution set. Okay, let's look at the next one. So let's go ahead and try to do this with tangents. So we're going to do our box and diamond. So we're going to get here in our box a negative 2x squared and a negative x there. So I think that'll be a negative 2 and a positive 1. So that means we're going to get our x squared here and our minus 2 there, and maybe the x's there, a negative 2x there and an x there. So we'll get x and x. This will be a negative 2. That'll be a positive 1, and it looks like that's going to work. So that's going to make it factor into tangent x minus 2 and tangent x plus 1 equal to 0. Now, the tangent x plus 1 equal to 0, I think we can solve because we don't need a calculator here. Now, tangent, remember, is sine over cosine. So if we ignore the negative sign for a moment, the sine and cosine are going to both be the same in quadrant 1 at pi over 4, where sine and cosine will both be square root of 2 over 2. We want them to be the same number but different in sign. That's going to make us be in quadrant 2 and quadrant 4. So that will give us in quadrant 2, 3 pi over 4, And in quadrant 4, that's going to be 7 pi over 4. Now the other one is a little different than any we've done before because this is not a known value. So we're going to have to now take an inverse tangent of 2 on our calculator. So I'm going to go to our calculator and go inverse second tangent of 2, and I'm seeing 1.107. 1.107. Now remember, our calculator is giving us that quadrant 1 angle. It's programmed for that, for an inverse tangent of a positive, but tangent will also be positive in quadrant 3. It's going to have that same reference angle, and so we want to go pi plus that. So we're going to go, I'm going to just take what's on my screen and go plus, and then a second caret symbol for pi, and that looks like 4.249. 4.429. Okay, now we got to do some checking here. So we are going to test, let's test 3 pi over 4. So we can take the tangent of 3 pi over 4, square that, minus the tangent of 3 pi over 4 minus 2, and ask the question, is that 0? Now tangent of 3 pi over 4 is going to be in quadrant 2. That's going to give us a negative 1, which we're going to square, minus a negative 1 and minus 2, and will that be 0? Well, 1 squared is 1, plus 1 minus 2, I think really is 0. So we're going to include in our solution set 3 pi over 4 as a valid solution. I'm going to go sideways here. So now we're going to test our 7 pi over 4. So we're going to again take the tangent of 7 pi over 4. We're going to square that, minus the tangent of 7 pi over 4, minus 2. Will that really be 0? So tangent of 7 pi over 4 is also going to be a negative 1 squared minus another negative 1 minus 2. And I can see, as before, that will also work. So our 7 pi over 4 is also going to make it into our solution set. Now it gets a little bit messier. We're going to try our 1.107. So we're going to take the tangent of 1.107, square that, minus the tangent of 1.107 minus 2, and wonder, is that going to be 0? So I'm going to go to the tangent, and then I'm going to go up arrow to that 1.107.148, blah, blah, blah. Put all of that in there, close the parentheses, hit the square button, minus tangent, up arrow again, and capture that 1.107, blah, blah, blah. Close the parentheses, minus 2, hit enter, and see that what I'm seeing on my screen is 3.0885. Then you're going to see that E, which is times, which means in scientific notation, times 10 to the negative 9. That means we would move this decimal point over 9 places. That, I think, is going to round to 0. So that means we are going to include our 1.107 in the solution set. Now let's try the next one. So now we're going to test x equals, what did we say that other one was? 4.429. 4.429. So we're going to again take the tangent of, and that 4.429, square it, minus tangent of 4.429 minus 2, and see if that's going to be 0. So I'm going to go tangent, I'm going to up arrow to find that 4.2487, blah, blah, blah. When I said 4, that's really a 2. Let me fix that. That's really a 2. 2 point, I mixed them up. So it's going to be a 4.249 and 4.249. Okay, so now I've got tangent. I've captured that, and so I'm going to close the parentheses, hit squared, minus tangent of up arrow to that 4.2 blah blah blah, close the parentheses, minus 2, hit enter, and that's going to be a negative 5.75 blah 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 times 10 to the negative 9, which is also going to be microscopic, which is close enough to 0 for us. So it too will make it into our solution set. So interestingly enough, we didn't lose any on this one. So those are all valid solutions. Okay. All right, let's do some multiple angle problems here. So we are going to get our secant 2 theta by itself. So we will subtract that 2 to the other side, and we will divide by square root of 3. We'll recognize secant as 1 over cosine. So we'll take the reciprocal of both sides, which will get us into familiar territory. So we'll say, well, cosine is square root of 3 over 2. Our reference angle in quadrant 1 is going to be pi over 6. Cosine will be negative in quadrants 2 and 3. So that's going to be a 5 pi over 6 and a 7 pi over 6. Now that would take us one time around the circle, but we're going to have to go twice around because of that 2 theta. So I'm going to add 2 pi to the 5 pi over 6. 2 pi is 12/6, so that's going to be 17 pi over 6. I'm going to add 2 pi or 12/6 to the 7 pi over 6 to get 19 pi over 6. We'll divide everything by 2, which is the same thing as multiplying by a half. So that'll become 5 pi over 12, 7 pi over 12, 17 pi over 12, and 19 pi over 12. And notice that is less than 2 pi, which would be 24 over 12. Okay, I think I'm going to just do one more. So I think this video is long enough, so I'm going to take that one off. And let's just do that last one over here. So we're going to say that tangent of 2 theta is a negative square root of 3. Now these are tough, so we know that if we ignore the negative sign and we want sine theta over cosine theta to be square root of 3, we can think of that as being square root of 3 over 2 over 1/2. So the same angle that makes sine equal to square root of 3 over 2 makes cosine a half, and will make tangent equal to square root of 3. So that is going to be pi over 3. Now we want the angles where tangent is negative. That's in quadrant 2 and quadrant 4. So that means in quadrant 2, we're going to get 2 pi over 3, and in quadrant 4, 5 pi over 3. That's one trip around the circle. We have to go twice because of that 2 theta. So adding 2 pi, which is 6/3, to 2 pi over 3, makes that 8 pi over 3. 6/3 plus 5/3 is 11 pi over 3. We're going to divide by 2, which is multiplying by a half. And so that's going to be just pi over 3 for that one. That's going to be 5 pi over 6, 4 pi over 3, and 11 pi over 6. All right, a lot on this one.